Hello, let's talk about stack, a commonly used data structure for algorithmic problems. To give some background, it's a data structure with LIFO, last in, first out, meaning the algorithm like pops elements which were added later first. So typically there are like three main operations: push, pop, and check if it's empty, but also it's often implemented as an array. And you can check what are the elements, like maybe second to the last, and so on. The problem involved in stack usually have some linear traversal. On each step, a number of items can be popped from the stack, and the current item can get added potentially. Since each item is pushed and popped at most once, the time complexity of algorithm would be linear. Stack can be good for problems dealing with brackets balancing or monotonous sequences search. And let's take a look at some examples. Classical problem is check if bracket sequence is balanced. So you have like open and close parentheses of one type. For this one, it's balanced if for every open there is a match in closing somewhere to its right, with each bracket used exactly once. Alternatively, we can define it if it's like empty string is balanced, and then if sequences A and B are balanced, and like A-B concatenation and like enclosing A and B into brackets also balanced. And you need to find if the sequence is balanced. So then the solution would be, let's have a stack and push open parentheses to it when we encounter them. When we encounter closed one, we try to pop open one. And if we cannot, because of stack is empty, then we declare the sequence imbalanced because hey, there is like closed parenthesis with no match. If in the end of the traversal the stack is not empty, we can also declare the sequence imbalanced because there are like some open parentheses which we couldn't find a match for. And also note that since in this problem we push same item to the stack, instead of the stack we can actually just keep a counter for how many open parentheses are not encountered in the closed one just yet. You can also find variations of this problem, like for example, what's the minimum number of brackets which need to be added to like balance the sequence, or you need to like actually return a balanced sequence itself. To do so, you just do some actions when you encounter an imbalance that cannot be like fixed. Like for example, when you try to pop from the stack and there is nothing to pop, then you know, okay, I need to add like one open parenthesis and so on. Let's take a look at a different example. Volume filled with water. This is a basin with n pillars, each of height hi. You can pour the water from the top until it spills to find how much water would be in the basin in the end. So here's an example. So we can see there's a couple of lakes. And on each index there is a different depth. Let's take a look at the solution. So each body of water will be limited by two pillars, where pillars in between have lower height. We can keep a stack with a monotonously decreasing sequence of pillars, I and hi. At each step we pop from the stack while the current pillar is higher than the last pillar in the stack, and add the volume water to the result based on the second to last element in the stack. Then we add to the current pillar to the stack and keep going until we reach the end of the pillars. So it's a very like short explanation, but let's take a look what it actually means. Let's get back to the picture. So suppose here we add this like pillar of height 5, then of 4, then of 2. So far there would be like no water, like if you look at these pillars only. But then the next one, like we add some and it's like higher than one before. So there is some room for water in between like this like second to last pillar in the stack right here and this current pillar, and the depth is going to be defined by the last pillar on the stack. So we kind of have like 3 pillars to work with at each step. You can think of like this like horizontal slices of water. So for example, here we just have like simple slice with one cube. So then we like add this, and then we add this like to the stack. So now stack has like this first, second, and fourth elements. So then like we encounter this big pillar that is gonna pop out everything from the stack. But again, we keep going like for next step, second to last is gonna be second one. So we're gonna have like delta of like widths would be like 2. which can hold the water, and then like depth of this slice would be determined by this like element which is like on the top of the stack right now. So it's gonna be like 2 total. Then we pop it from the stack, and then the second to basically second to last would be this like first pillar, and then again we get this slice of horizontal of like three like things, and then we pop everything from the stack, and then we like kind of repeat the process again. We kind of just add this like 1 to the stack, then like when we add this what's this 7th element, we again like we can pop this like last element from the stack, and it controls the height of this slice, and the like width of the slice is between like second to last element of the stack, which is this like 5th one and the 7th one. And then again in the end we just also like do another pop, and we add another slice of water, which is between like 5th and 8th elements. And then we add 8th element to the stack, but then there is like nothing we can add on top because there is no limit in pillar, and that's so that's all they're gonna be in the answer. Yeah. So some homework. Feel free to do it yourself. I'm gonna be doing analysis like after some pause. So let's go over the problems. So first one is also like about balanced sequences of brackets, but now we have 3 types of it. And before you use counters, beware that there is a tricky case. For example, open like regular bracket, open square bracket, close regular, close square. So counters are just not gonna work for this one. Another one is like some calculator. There are like variations of this calculator problem, but this one would be with like numbers, plus, multiplication, and brackets. And then last one, given an array with n integer, find next greater element for each element in this array. And it's like you want to have linear time. Okay, I'll make a like short pause. Feel free to pause the video and go try to like solve those problems. Okay, let's do analysis of the homework. So the first problem is like very similar to what we did with the stack. So we keep adding open parentheses to the stack. And when we encounter a closed parenthesis, we check, okay, what's the parenthesis on the stack? And do they match? Like for example, if we encounter like a regular bracket and a square bracket closing, then they don't match and like sequence is imbalanced. But if they match, we pop the open one from the stack. And in the end, similarly, like if we have like non-empty stack, then it's imbalanced, and if we cannot pop anything, it's also imbalanced. Yeah, calculator. So we're gonna be using the stack to like pop elements to expression just to like check the order of evaluation. So if you have a number, we just see what's on the stack. If it's last like element was like multiplication operation, then we can like just multiply it by a previous number on the stack and just put the result in the stack. If it's plus, then we don't know. We for example can have like 1 plus 2 times 2. So in encounters the first 2 we just don't know, so we don't evaluate it, we just add it to the stack. If we encounter open bracket, we just like add it to the stack. When we encounter a closed bracket, so the way we do it, we just have like basically a lot of additions on the stack until we encounter a previous like matching open parentheses after when we have closed one. So we just like pop them from the stack and do those additions and add the result to the stack, and that's gonna be like that little block of like parentheses. So in the end, in the stack we're also gonna have like some parentheses, open parentheses, we have numbers and like plus. Yeah, and then in the end, don't forget to empty the stack and just like compute. We should have some like basically additions to do. And if you, for example, don't have brackets and just have a simpler variation of this problem, then You don't really need a stack. You can kind of like keep a track of, hey, like what the element you have. If, for example, there's a plus, you can keep the second element. There's multiplication, multiply the second element and like keep it as a second. But if there's another plus, you can like you can add the first element to the sum and then just shift the variables, meaning so then like you can keep like be in a similar situation. So you can have like just essentially this variation of like simple stack with couple of elements, but you can also do this approach with a stack as well. And then the last problem, so with array and an integer, find next greater element for each element in this array. So we're gonna apply a trick to go from the back actually. And then we, on each step, like for the last element, we just don't have a next element at all. So next greater element would be like something like -1 or just like none, depending on how the problem like asks you to like denote that. But then we add it to the stack. Then we take a look at the second to last element. Then if it's smaller than the element at the top of the stack, we just like mark it as, hey, for this element, then mark position of the next element, like greater element, and then like add this like current element to the stack. If the current element is bigger than like element on top of the stack, we just keep popping from the stack until it becomes like smaller, or in like if we pop everything from the stack, then that means like for the current element there is no next greater element, so again it would be like -1, and then we just add it to the stack. And this way we can construct this result for like all n elements in a linear time. That's gonna be it for me for today. Thanks for watching. Let me know if you have any questions.